And welcome back. As we go ahead and continue learning about linked lists, let's go ahead and take a minute to pause to actually look at the runtime inefficiency of our algorithms that we have worked with to this point. So the first thing we're going to look at is program speed. If you were to go and ask a program, for example, how fast his or her program is, you might expect an answer that says, it takes me 2 seconds to run this code. However, the speed of a program cannot be given by a single number. A program is typically going to take a longer amount of time based upon larger inputs than it would based upon smaller inputs, which makes sense. You have more data to process. You would also expect a program for sorting numbers, for example, to take less time to sort 10 numbers than to sort 1,000 numbers. Again, the same idea. You have a larger number set, you're going to take longer to get through it. Now, perhaps let's say it takes 2 seconds to sort 10 numbers, but it's going to take 10 seconds to sort 1,000 numbers. So when we start looking at determining speed here, one thing you'll notice, if you look at this table here, you can see that as we start sorting these number sets, you see that the number of seconds starts climbing higher and higher, especially as our number of numbers to sort is getting larger and larger by a factor of 10. So if we ask our programmer, again, that same question, how fast is your program? Well, this table of values might be a good way to show how long that program takes based upon the size of those values that you're trying to have it process. And if you look at the table, you notice that we don't have a single time. There's no consistency with this time. Like we have 2 seconds, 2.1 seconds, 10 seconds, 2.5 minutes. All right, and you'll notice that these times vary based upon the input sizes. Now, that means that we're having to look at this with a function, all right? Inputs and outputs, which is what we would be familiar with in mathematics. All right, just as in Java, we have, let's say, a non-void method is going to take in an argument and then return a value. So does the function take in an argument, which in this case is our input size, and returns a number, which is the time the program takes on the input of that size. So let's just say we call this function t. Well, then we can say t of 10, it would be 2 seconds, t of 100 is 2.1, t of 1,000 is 10, and t of 10,000 is 2.5 minutes. The table, of course, is just an example, right? We're just looking at some sample sizes. And obviously, we could have inputs of every size. I could say, hey, how long am I going to take for an input of size 5, or an input of size 500, or an input of 127. Obviously, we could plug those in here. And although they're not shown, we do have values for, like I said, every kind of input, t of 1, t of 2, etc., so on and so forth, until you have used every possible input that would be for that function. And let's just say for any positive integer, because we're going to assume we're plugging in positive numbers here, t of n is the amount of time it takes for the program to sort n numbers, and that function is therefore called during the runtime of the program. Now, obviously, if we look at this, we have different things, and we start asking, well, what's the worst case runtime? What's it going to be the worst possible scenario when we use these large numbers? And up to this point, we're assuming we're using a sorting program. It could be a bubble sort, selection sort, doesn't matter. And let's just assume that it's going to take the same amount of time on any list of n numbers. Well, this doesn't have to necessarily be true, because perhaps it takes much less time if that list, for example, is sorted, or it's almost sorted. Obviously, it's got less steps for it to work through. All right, we're not assuming every number is scrambled in any possible way. We're just saying, hey, maybe we have a list that's already partially sorted. Well, what does that end up doing then with our sorting algorithm? Well, in this case, remember, t of n is defined to be the hardest list, all right? That is pretty much you can think of like the maximum number of steps it would take n numbers, to make that program run for the longest duration. This is what's known as a worst case runtime. So when we're looking at sorting algorithms, which is where some of these cases come from, we start asking, how long does it take for us to sort something, or for us to traverse something? How long does it take for that algorithm to execute? And the worst case, of course, is assuming we are least optimized. We don't have, for example, when we looked at our sorting list, we said things aren't sorted. It's all in random values. There might be all sorts of mix-up that we were going to have to go through the entire list to sort it. And for now, when we start looking at Big O and runtime in this lesson, we're going to assume that we're looking at this from the lens of a worst case runtime when we're looking at our algorithms or for any kind of code that we're going to use. Now, obviously, formulas are going to play a factor in this, all right? So let's just say the time taken by a program or algorithm is often given by a formula. That formula could be something like 4n plus 3, 5n plus 4, maybe n squared. It just depends on what algorithm you're using. Now let's just say our running time algorithm is 5n plus 5. Well, if we have inputs of size n, the program will run for 5n plus 5 time units. Now, if we look at this line of code, this is simply just searching an array, to determine whether or not a particular value is in the array. We say int I equals 0, boolean found equals false, while I is less than n and it is not found. If a of I, so it's looking to see if that value is the target, or target value, well, we're going to set found to true, all right, and then obviously that would of course affect our loop, else I++, so we're going to iterate through to the next value. So how long, right? How long is it going to take the computer to execute this code? And so we might say, we want to have some kind of estimate where we could go through and determine what that value is. Well, we would like an estimate that does not depend on which computer we use, for example. All right, we don't necessarily want this to be machine dependent. Either because we don't know what computer we're going to end up be using. It could be a top of the line gaming laptop, or maybe it's just this little tiny Chromebook. All right. Either way, we're going to have several different computers to run that program at different times, and that's going to, of course, affect our estimates. Now, one possibility, and we've kind of looked at this before, is to count the number of steps. But it's not necessarily easy to decide on what a step is. One of the things that we looked at in the past when we looked at the efficiency, for example, of bubble sort versus selection sort, is we use a simple counter variable that simply kept track of the number of times that the sorting call was called. In this situation, though, the normal thing, of course, is count the number of operations. Which again is very similar to that count variable that we did before. Now, the term operations is kind of vague if you think about it, but there's some agreement in practice of what qualifies as an operation. So when we look at those operations, we start asking about carrying them out. Let's just say in the Java code, each application of the following would count as an operation. So whether we're using an equals, which is an assignment statement, less than, and, not, any kind of brackets, equals to, and plus plus. Those are all operators that we can do. So the computer must do things besides carry out these operations, but these seem to be the main things that it is doing if we look at that line of code that we had previously, and assume they account for the bulk of the time needed to run that code. In fact, our analysis of time will assume that everything else takes, let's say, no time at all in comparison, and that the total time for a program to be run is equal to the time needed to perform whatever operations we have laid out in front of it. Now, this is, of course, a little bit of an ideal situation, so it's not completely true, and it, may not be 100% accurate. However, it turns out that if we simplify this assumption, it works well in practice, and this is often made when analyzing either a program or an algorithm. So let's start talking about considering the different cases that we're going to have to work through. So even if we simplify our assumption, we still have to consider two cases with the current sorting algorithm that we're looking at. Either the value target is in that array, or it's not in the array. So if let's say the array is 1, 2, 3, 4, 5, and we're looking for the number 10, well, 10 would not be in that array. So let's first consider the case when the target is not in the array. So we're saying, okay, this number is not in the array. What do we need to do? Well, the number of operations performed will depend on the number of array elements searched. Because obviously if we have to traverse the whole array, that's going to be very different than if we have to traverse, for example, half of that array. The operation equals is performed 2 times before that loop is executed. And because we're assuming the target is not in the array, the loop will be executed n times, 1 for each element of the array. Now, each time that loop is executed, the following operations are performed. We have a compare, we have inequality, we have a and, not, we got our brackets, etc. This adds a total of 5 operations for each of the n loop iterations. Finally, after n iterations, the Boolean expression again is checked and found to be false. All right, so which is adding a final 3 operations, because again, we're going to have to do that check there. Now, if we tally all these operations, all right, one thing to get is the algorithm has a total of 6n plus 5 operations when that target is not in the array. Now, we're going to leave it as an exercise to confirm whether or not the target is in the array, then the number operations will be 6n plus 5 or less. So let's leave this for later. We'll think about this when we'll come back to it. However, the thing we do want to look at right now is saying, hey, our worst case runtime, so the worst possible scenario that we could run into, is 6n plus 5 for any operations of the array of n elements and any value of target. Now, we just determined that the worst case runtime for our search code is, of course, 6n plus 5. But an operation, though, is not a traditional unit of time, such as, let's say, a nanosecond, or even a second, or a minute. If we just want to know how long the algorithm is going to take us to compute, we need to know how long it takes that computer to perform an operation. It kind of goes back to that earlier question of asking your programmer, how long does it take for your program to run? So if an operation can be performed in 1 nanosecond, then the time will be 6n plus 5 nanoseconds. If an operation can be performed in 1 second, well, it's 6n plus 5 seconds. All right, if it's, let's say, a really slow computer and it takes 10 seconds to perform an operation, then the time would be 60n plus 50 seconds. So we start approximating our runtime here. In general, it takes the computer, let's say, c nanoseconds to perform one operation. Then the actual runtime will be approximately c times 6n plus 5 nanoseconds. Now we say approximately because we're making some very simple assumptions here, and so this assumption may not necessarily equal the result that would be our true running time. This means, again, 6n plus 5 is a crude estimate. If we want to get the runtime expressed in nanoseconds, of course, we have to multiply by some constant that depends on the computer that we're using. So again, remember 6n plus 5 is only accurate to within a constant multiple. So as soon as we start bringing some of the other factors in, it's going to change things. Now, this gets back to our topic at the very beginning, which is that of big O notation, which I've already mentioned. We've talked about a little bit already. But what does that mean? Well, if we look at how we analyze big O notation and runtime analysis, all right, you might recall that big O is looking at worst case runtimes, which is what we just talked about and looked at with our previous example here. Now, what does that mean if we start looking at it in context of our data structure? So the various different things, like obviously array is one data structure, but it's a primitive one. Well, estimates on runtime, such as the one we just went through, are normally expressed, therefore, in big O notation, because again, remember, we're looking at this through the lens of a worst case runtime. Suppose we estimate the runtime to be, let's say, again, 6n plus 5 operations, and suppose we know that no matter what the exact runtime of each different operation may turn out to be, there will always be some constant factor, c, such that the real running time is either less than or equal to c, which is, again, 6n plus 5. So we have a function. What's that big O of it? Well, if we look at that function, we say, hey, the code or the program or the algorithm is running in big O of 6n plus 5. All right, so that is what we call the big O of that function. We don't necessarily need to know what that constant will be, because the constant is not necessarily something that is necessary in the big picture as important. While it might be undoubtedly different for different computers, we must know there's one constant c for any such reasonable computer system. If it's very fast, c might be less than 1. So let's just say 0.001. All right, that's not going to affect that algorithm quite as much. If it's very slow, c might be very large. Let's say 1,000. Obviously, that's going to have a different kind of play in it. More because let's say we start changing units from, let's say, nanoseconds to seconds. This involves only constant multiples, so there's no need to give any units of time, because you notice that when we say big O of 6n plus 5, we're not saying it's a unit of time, because again, we're using this with a different unit than we might traditionally utilize. Now, one thing that we need to talk about is the upper bound estimate. One thing is that with big O that we have to notice is the upper bound estimate, which is a big O estimate. We always approximate this by taking numbers on the high side rather than the low side of what we consider to be the true count of that function. Notice that when performing a big O estimate, we do not need to determine an exact count of the number of operations performed. We only need an estimate that is correct up to a constant multiple. If our estimate is twice as large as the true number, well, that's good enough. And this, of course, is leading to us our conversation on the order of magnitude estimate. So an order of magnitude estimate, such as our previous 6n plus 5, contains a parameter for the size of task solved by the algorithm or program or some piece of code. In our sample case, this parameter n was the number of array elements to be searched. Not surprisingly, it takes longer to search a larger number of array elements than it does to search a smaller number of array elements. I mean, most people would assume that if you have 100 or something, it's going to take you longer to do it than if you had 10. Now, big O runtime estimates are always expressed as a function of the size of the problem. And for now, all our algorithms will involve a range of values within some container. However, in all cases, n is going to be the number of elements within that range. Just keep those little things in the back of your mind. So when we start looking at some big O graphs, like what does this actually look like in terms of runtime? Well, if we look at the graphs to the right, you'll notice that all the graphs of the function that are big O of n eventually fall below the graph of the function 0.5 n squared. So this is our function right here. So you can see this one is growing the fastest, whereas these are all pretty constant. We have t of n equals n. We have t of n equals n plus 2. We have t of n equals 2n. All right, so we have a pretty inevitable result here. The big O n algorithm will always run faster than a big O of n squared algorithm, provided we use large enough data values. All right, these are always, once we hit this threshold here, right here at this data size, these are going to go faster. There's just no way around it. And although a big O of n squared algorithm could be faster for a big O n algorithm for that problem size, you notice right here underneath, this is always going to be faster, especially right here in the beginning. Often you'll find that programmers have found that big O of n algorithms perform much better than big O of n squared algorithms for most practical applications that are intuitively pretty large. Like if you're only using, for example, 10 numbers, yeah, you may not notice it as much with an n squared algorithm, but if you have something that's big O of n, obviously you can see that there's some advantages as your data starts getting larger. Data is smaller, it probably won't matter as much because let's say you're, again, only using 10, you're not having to necessarily account for quite as much data. Now, similar remarks can apply to any two different big O runtimes. So if we start bringing in other big O notations, so let's just say big O of 1, or let's say big O of log x, how are those going to change this conversation? What are those going to look like if we actually start graphing those? So ultimately, it comes back to our conversation on runtime. So just to give us a recap, some terminology is going to help with descriptions of generic algorithm running times. So the first thing to understand is a linear running time means a running time of t of n equals an plus b. This is a big O of n runtime. So it's always going to have this mapping. And the way to think about this is like, if I were to get rid of this a, get rid of this b, what am I left with? I'm left with n, so it's a big O of n. Now, quadratic would mean that we're running the highest term of n squared. So quadratic runtime is always big O of n squared runtime. Now, I already mentioned a little bit what about logarithmic. What about logarithmic running time? Because obviously the main two examples, we had a linear and we had a quadratic. Well, occasionally you're going to have more of logarithmic functions in your runtime. Now, those are normally given out any base because change base is just constant multiple. So if you see a log n, think log base 2 of n. It's not going to be wrong to think log base 10 of n either, because again, these are very similar functions. Logarithms are very slow growing functions. And whereas like a big O log n, we look at this, let's say from the runtime perspective, well, they're going to run very fast because their growth rate is going to start and then it's going to kind of flatten out. In many cases, our running time estimates will be better than big O estimates because that's again how the running time algorithms work. Now, when we specify a linear running time, that's a tight upper bound. And you can think of the running time as being exactly t of n equals constant times n, although that c is still not specified. So this is just more stuff for us to wrap our mind around is how these big O functions are looking. And let's wrap this back up now finally with our conversation on linked lists, because that's been our main focus. So with linked lists, if we think back to big O, how can we express the efficiency of various methods for linked list structures? Well, as an example, analyzing the runtime efficiency of an algorithm, considering the find method that we have in our class linked list 1. This method starts at the head of the list and sequentially iterates through each node to see whether or not it matches the target. If the linked list contains many nodes, then we might get lucky if the target is found in the head of the list. In this case, the computer had only to execute one step, check the head of the list for the target. In the worst case, the computer might have to search through all n nodes before finding, or not finding, the target. In this case, the computer, of course, had to take extra steps. The worst case would be, obviously, taking longer to execute than that of our best case. All right? And it makes sense because, we're having, again, coming down to the number of steps we got to do. The worst case is always going to end up taking longer. Now, what does this mean for a linked list runtime? Well, with the linked list runtime, on average, you can expect to search through roughly about half the list before you find your target, because most of the time it's going to find it pretty quickly. This means it's going to require n over 2 steps. In our big O notation, the find operation would be big O of n, because that's the same. If we look at n over 2, well, that's the same as 1/2 times 2. And remember, I said that a variable doesn't matter as much because we're just simply looking at what is really kind of the exponent that's attached to that. So that's how we get big O of n. However, the add to start method requires linking only a few nodes to the head of the list. This is actually run in big O of 1 steps. That is a constant upper bound on the runtime limit that's independent of the size of the input. Now, we aren't going to tackle this today, but in the upcoming lesson, we'll explore a few other data structures that require fewer steps because obviously we want to have as few steps as possible in order to keep that runtime down.